All right, so this example problem reads, monochromatic light falls on a slit whose width is 2.6 times 10 to the negative third millimeters, so super tiny. If the angle between the first dark fringe and the next dark fringe over center is 29 degrees, so the fringe to fringe is 29 degrees, what is the wavelength of light? So this is the idea of if I can measure the diffraction grating and I know information about my system, like the width of the slit, I can determine what wavelength of light I'm dealing with. So let's draw a picture to kind of visualize what we're talking about here. So here's our slit. Here's our screen, and again, we imagine this being really far away, right? I'm not able to draw it that way. And if we see here's our center right at that. So that's our maximum. And there might be the fringes on the sides, the additional light. We're really interested in this sort of darkness to darkness area. So we're told that the angle in the problem, the angle between these two is 29.0 degrees. So that's what the problem is describing. All right, so the question is, what is the wavelength of light? Our question is, what is the wavelength? This is the width of that center, as described in the problem. 29 degrees is the angular width. What is the wavelength of light? So we have to recognize a couple of things. We know that the first dark fringe is given by the equation d sine of theta is equal to m lambda, where m is equal to 1. So we know we have d sine theta is equal to lambda, the first fringe. Now what does this theta mean? That is the angle, remember, the angle at the light is entering that slit. Not this 29 degrees, it is the angle plus or minus to that first fringe. It's this angle. That's the angle theta that we're dealing with, all right? So that tells us that 29 degrees is equal to 2 times theta that we're interested in, or theta is equal to 14.5 degrees. So that's the theta that we're interested in. Now we can use our equation to solve for lambda. So I'm just going to rewrite that equation. Again, m is 1 in this case. So d is, what's our d is 2.6. I know it's up there, but I don't see that. 2.6 times 10 to the minus 3 millimeters times the sine of 14.5 degrees. That equals our wavelength, and we find our wavelength to be 6.5 times 10 to the minus 4 millimeters is equal to lambda, and that is also equal to 650 nanometers. All right. So recognizing what we're dealing with, and then looking at our relationship for the dark, where the m's are integer values, and recognizing the angle that we need and solving for the wavelength. Good job.